Well, hey everybody, I'm Dr. Mark Hatala, and I'm lecturing to you today from the conference room, which is across from my lab and next to my office. And today we're going to be talking about why we need statistics and what type 1 and type 2 error are. And so let's get started by saying, well, I don't need to write it on the board. The reason why we need statistics is so that everyone is dealing off of the same deck. And so if somebody tells you that they're doing, let's say, a t-test, you know what that is and you can replicate a t-test. Or if they're doing a multiple regression, then if you had the same data, you'd be able to do the same study. Now, there are 4 steps in how we do statistics, so how it all works. The first thing that we need to do is get a sample. Maybe I'll put statistics at the top. So get a sample. And that could be a random sample. It could be a matched sample. But it's probably a convenience sample. So that's pretty straightforward and easy. Everybody knows how sampling works. The second thing that we do is state a null hypothesis. And the null hypothesis, so let me say this too. I wish there was some standardization in statistical nomenclature, but there is not. And so the null hypothesis is usually represented as H sub 0. And what it's saying is that the independent variable has no impact. It has no effect. No statistically significant effect. Okay. And so that's the way it's presented as, it's usually represented in terms of means. If you're talking about a t-test, so mean 1 minus mean 2 is equal to 0, that there's no difference. Actually, I'll write that up as an example too. So mean 1 minus mean 2 is equal to 0 would be a good example of a null hypothesis. What is the independent variable in a study like this? Well, it could be giving caffeine to people and then measuring their heart rate. So you're saying the people who get caffeine versus people who just get water, that there's no difference between them in terms of their heart rate. Okay. The alternative hypothesis is sometimes H sub A. I prefer H sub 1. And that says the independent variable has a significant impact. Okay. And this could be what's called bidirectional, where we say mean 1 minus mean 2 is not equal to 0. Or it could be a directional hypothesis too, where we would say mean 1 minus mean 2 is greater than 0, or mean 1 minus mean 2 is less than 0. And we can always remember greater than and less than. It was true in 2nd grade, it's true today. The alligator always wants to eat the bigger number. That's exactly right. One of the truisms of childhood. So that's the second thing that we want to do, is state a null hypothesis. I'm going to erase all this. I need a larger whiteboard. Usually I have a whole classroom wide one, and I can write everything up. But you can always pause this if you like. The third thing that we need to do is choose a significance level. And this says, how often does something have to occur for us to say, hey, that's significant? Now, the gold standard in social science, which is kind of a humorous statement, is 0.05, which is 5% of the time, or 1 time in 20. If something happens that often, we're like, well, that's significant because we weren't expecting that result. We can go with a more stringent significance level too. We could go with 0.01, or 1% of the time we're going to say that's significant, or 1 in 100, or we could go with 0.001, and sometimes you see that, which is 0.1% or 1 in 1,000, which is a very stringent significance level. Again, in the sciences like chemistry and biology, these are kind of laughable, but in social science, this is what we use. And there's ramifications for the significance level that you choose. The fourth thing that we do is we state a conclusion. And we can only state two different conclusions, and they're both in terms of the null hypothesis. We can either fail to reject the null hypothesis, or we can reject the null hypothesis. Okay, we never fail to reject the alternative hypothesis or reject the alternative hypothesis. It's like we're always laser focused on that null hypothesis, because the null hypothesis says that there is no impact of our independent variable, and we want there to be an impact, and so we want to be able to reject the null hypothesis. Okay, well, now we get into the issue. Let's complicate it one more level. Now we get into the issue of type 1 and type 2 error. Okay. Type 1 versus type 2. So here's the issue, okay, is we may reject the null hypothesis or fail to reject the null hypothesis, but we might be wrong in the conclusion that we state, okay? So I'll chart it up because charts always make things easier to understand. So for example, here's us. You, me, Joe Bag of Donuts. We have two choices. We can either fail to reject the null hypothesis, or we can reject the null hypothesis. That's it. Those are our two choices, okay? Up here is the correctness of the null hypothesis. So the null hypothesis, in reality, we'll say reality, and then you can determine who decides what reality is. Maybe it's the number of people who are conscious of something, maybe it's a supernatural being. I'm not here to lecture on that. So the null hypothesis is either true or false. In reality, it's either true or false, okay? So I'll talk about this in general, and I'll give you a specific example. Actually, I'll give you two specific examples for the price of one. If we fail to reject a null hypothesis, and it is in fact true, that's correct. So the null hypothesis was true, and we didn't reject it. What's the probability of that? It's 1 minus alpha. And so if we set alpha at 0.05, there's a 95% chance that we are going to fail to reject a null hypothesis that's actually true. What if we reject a null hypothesis that's true? Well, that's not good, and that's a type 1 error. So the null hypothesis is true, but we rejected it, okay? So this would be a false positive. Okay, what's the probability of making a type 1 error? It's alpha. And so if you set it at 0.05, then you're going to make that error 5% of the time, 0.01, 1% of the time, 0.001, one time in 1,000, okay? Here's the problem, though, is there is a trade-off between type 1 error and type 2 error. Type 2 error is when you fail to reject a null hypothesis, which is actually false. So it is a false negative. So the null hypothesis is false, and we didn't reject it. That's a problem. What's the probability of doing that? It's equal to something called beta, which is impacted by the size of our sample size, so how many people we're running. But that's a type 2 error. And then if we reject a null hypothesis, which is actually false, then that's also correct. And the probability of that is 1 minus beta. You don't need to know this until you're in higher statistics, how to calculate beta. It's tied to what the impact of the independent variable is. If we think it's going to have a large impact, then we only need a few people. If we think it's going to have a small impact, we need a lot of people. And so it gives us a number. How many people do we need to correctly reject a null hypothesis, which is in fact false, which is what we want. So this is like the what we want category. Okay, let's put this into a specific experience. What I have here, actually I have 2 tests here. This is an at-home marijuana test that was given to me by a student. I know it's a marijuana test because it says marijuana there, and then I believe this plant is a marijuana plant. I wouldn't know. But let's not talk about that. Let's talk about pregnancy tests, because I hand this around in class when everyone's present, but I got this, this is from Walmart. It's an Equate brand, because why spend more on a pregnancy test, you know? And it either gives you a plus, which means that you are pregnant, or a minus, which means that you're not pregnant. And it says it's over 99% accurate, which seems pretty accurate to me. So that means it's the alpha's at 0.01. Okay, so what does this mean? Well, the first thing that we have to determine is the correctness of the null hypothesis. So what is our null hypothesis? Is it that you're pregnant or that you're not pregnant? Well, think about your people in your own family, okay? So your moms, do they spend most of their life pregnant or not pregnant? Even if they have a lot of children, they tend to spend their lives not pregnant. So if I know nothing else, I can say chances are they're not pregnant, okay? Sometimes people are pregnant, but so that's our null hypothesis, is that you're not pregnant. And at our health center, if you're a woman and you go in, they always ask you, is there a possibility that you might be pregnant? And so I was raised Roman Catholic, so there's always a possibility that you could be pregnant. Virgin birth is a part of our religious beliefs. So here's us over here. Oh, so if it's true, the null hypothesis is true, you're not pregnant. If the null hypothesis is false, then you are pregnant. Okay, so we're clear on that. Failing to reject a null hypothesis means that you're saying it's not pregnant. Okay, so it comes up negative. Rejecting the null hypothesis says that you're pregnant, and so the test comes up positive. Okay, so if we have the ground rules in place, if a pregnancy test tells you you're not pregnant and you really are not pregnant, then that's correct. If a pregnancy test tells you you are pregnant when you're not pregnant, that's a false positive. So that's type 1 error, a false positive. It's not good, but we can debate this here in a minute. If a test tells you you're not pregnant and you really are pregnant, that's an issue too. And so that's a type 2 error, a false negative. And if the test tells you that you are pregnant and you really are pregnant, then that's what they always portray in the pregnancy test commercials, where everybody's very happy about it. And so that's correct. And you're going to have a baby, and that's kind of fun and nice too. So here's the question, is what is it worse to make? A type 1 error where you tell people they're pregnant when they're really not pregnant, or a type 2 error where you tell people that they're not pregnant when they really are? Well, this has been settled through litigation because it says right here on the pregnancy test that it's 99% accurate. So that seems like, well, that gives a sense of security, doesn't it? Here's the thing, is that pregnancy tests almost never give you a false positive. So they avoid a type 1 error, okay? Why? It's due to litigation. Because if the pregnancy test tells you you're pregnant and then you change your behavior in some way or harm yourself, then they're liable because they told you were pregnant when you really weren't. And you might say, well, false negative is pretty bad too because then you're not taking care of yourself. But it's difficult to prove that you would have taken care of yourself had you known that, that you were actually pregnant. So, if a pregnancy test tells you that you're pregnant, what does that mean? It means you're absolutely pregnant. There's a 1 in 10,000 chance that you're not pregnant because these are 99.99% accurate. I'll put that up here too, 99.99% accurate. So really what a pregnancy test tells you is whether you are pregnant or that you may be pregnant, okay? You should never get any sense of security from a negative on a pregnancy test because all it means is maybe you're not pregnant or maybe there's a false negative. Yeah, so it says baby or maybe baby, not no baby. So that's my pregnancy test example. I want to give you one other example which is far less interesting, which is signal detection. Okay, and this comes from we gotta move this stuff out. Here we go. This goes back to, this is signal detection theory. Because the question that we always have to ask is it worse to make a type 1 error or a type 2 error? A lot of textbooks say it's worse to make a type 1 error because we can control it through alpha. But like everything in life, it depends, okay? It's situation and context that determine what's good or bad. So signal detection theory comes from, or at least how it applies here. In the 1950s, there's something called NORAD, which is U.S. missile defense, where people are looking at screens, radar screens back in the day, and they're trying to determine what something is. Is it a missile or is it just a flock of birds because they can look similarly on a radar screen in the 1950s? Now, the Null Hypothesis is that it's going to be birds because there's never been a missile fired at the United States as of this recording. If the Null Hypothesis is true, it's birds. If it's false, it's a missile. And as someone who grew up in the 80s, we would be afraid of missiles, that the Soviets were going to nuke us all the time. If we fail to reject the Null Hypothesis, we're saying it's birds. If we reject the Null Hypothesis, we're saying it's a missile. Okay, so if we say it's birds and it really is birds, that's correct. If we say it's a missile and it's really birds, that's type 1 error, false positive. I don't know why I erased this, now that I think about it. Does this mean it's the end of the world, like we just launch our missiles? No, it means that we send up aircraft to get visual reconnaissance and see if that really is a missile or if it's just a bunch of birds. What if we say it's birds and it's really a missile? That's type 2 error. That's a false negative. And if we say it's a missile and it really is a missile, that's correct, but it's very bad. Here's the question. What is it worse to do? Make a type 1 error or a type 2 error? Well, in this case, there's no real question about it. It's worse to make a type 2 error because you're thinking everything's fine and really it's an upcoming disaster. And so you're completely caught unawares An example of this that I can give you, they had radar stations at Pearl Harbor on December 7th, 1941, and they did see some blips on it, but they thought it was a group of B-17s who were coming in from California. In reality, it was the Japanese Navy, and that's what happened with Pearl Harbor. So that's what I want to talk about in terms of type 1, type 2 error, how we do statistics and how it all fits together. I hope you're having a great day wherever you are, and I'll talk to you again soon.